Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at tree diagrams without replacement. So in a previous video, we looked at tree diagrams with replacement. We discussed that tree diagrams are used in probability when you have a multi-stage event. The point of tree diagrams is to list all the possible outcomes. So if we look at this example, we have a bag containing 7 cola, 5 watermelon lollipops. We're going to pick 2 lollipops, one after the other. This is a multi-stage event. Picking the first lollipop is the first stage. Picking the second lollipop is the second stage. So we learned on a previous video how to make a tree diagram. We just list the possible outcomes. First pick, you can pick cola or watermelon. Second pick, you can pick cola or watermelon. The point of this tree diagram is so you can list all of the possible outcomes. So here we have 4 possible outcomes: first stage, second stage. So we also discussed in previous video that sometimes the final outcomes won't be equally likely. We can't say that each of these events has probability of a quarter because they are not equally likely. The reason they're not equally likely is because at each stage there are more cola than watermelon lollipops. You're more likely to pick a cola than a watermelon. So how do we find their probabilities? Well, we discussed also in a previous video that what we do when the events aren't equally likely is we put probabilities on the branches and then we end up multiplying them. So for the first pick for cola and watermelon, the probability of getting cola is 7 over 12. There are 12 lollipops, 7 of them are cola, and 5 out of the 12 lollipops are watermelon. Now, what we need to do to finish this question is we need to understand the difference between with and without replacement. On the previous video, we looked at this exact example when the lollipops were picked with replacement. So with replacement means if you pick a cola the first time, then you replace it with a cola before you pick the second lollipop. Similarly, if you pick a watermelon, you would replace it with another watermelon before you pick the second lollipop. When we did this tree diagram and the picking was with replacement, the probabilities were the same for the second stage as the first. It was 7 over 12 for cola, 5 over 12 for watermelon. But when they're picked without replacement, the probabilities here change. So if you pick a cola first go, there were 7 out of 12 colas, but if you get a cola first go, then there are only 11 lollipops left and 6 of them are cola. So if you pick a cola the first go, you only have a 6 out of 11 probability of picking cola the second go. If you pick a cola the first go, well, there's 11 lollipops left, but there are still 5 watermelon left. At each stage, these probabilities should add to 1. So if you pick a watermelon first go, then there will be 11 lollipops left and there will still be 7 cola left. If you pick a watermelon first go, there will be 11 to choose from the second pick, but there will only be 4 watermelon left. Once again, you've got to make sure they add to 1. So this tree diagram looks very similar to the tree diagram when we did this example with replacement. The only difference between with and without replacement are these numbers here have changed. When we did with replacement, it was 7 over 12, 5 over 12, 7 over 12, 5 over 12. But when it's without replacement, your probability of getting cola the second go is not the same as getting it the first go. Similarly, the probability of getting watermelon the second go is not the same as it was the first go. So when things are done without replacement, the probabilities change at the second stage. So that is literally the only difference between with and without replacement. Otherwise, the tree diagram is the same and the process is the same. So remember we learned on that previous video, to find the probability of each of these 4 outcomes, we multiply the numbers on the branch. So the probability of cola then cola is 7 over 12 times 6 over 11. And that actually gives us 7 over 22. The probability of getting cola than watermelon is 7 over 12 times 5 over 11, which is 35 over 132. So similarly for the last two, to find their probabilities, just multiply the numbers on the branches. So these four probabilities should add up to 1, and you can see the probability of each of these is not 1 over 4 because they are not equally likely. So the probability that you pick one kind of each lollipop, you can either get cola then watermelon or watermelon then cola. I can get either of these two events. So remember, you multiply the branches to find the probability of each of the outcomes. Then what you do is find which outcomes satisfy the question. In this case, the question was one of each kind. These two satisfy that. They're one cola, one watermelon. You find which ones in the list of outcomes satisfy the question, and you add up their respective probabilities. So the final answer to this question is 35 over 132 plus 35 over 132. These two added together gives 35 over 66. So we saw on the previous video, when this exact experiment was done with replacement, the probability of getting one cola, one watermelon was 35 over 72. So the probability of getting one cola, one watermelon is slightly higher when this is done without replacement. But with and without replacement tree diagrams are exactly the same, except the probabilities on the second stage are a little bit different. Other than that, the process is the same. You list the outcomes at each stage, then you use that to list all of the possible outcomes of the experiment. If each outcome is not equally likely, you write the probabilities on the branches. To find the probability of each outcome, multiply the branches. Then to answer a probability question, find which of the outcomes in your list satisfy the question and add up their respective probabilities. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.